I assume so. All right. So welcome everybody to this part of the Antennas and Propagation e-seminars dedicated to RCS. So it's scattering time now. And after a quick introduction of the main concept and definition of the RCS word, we'll deep dive into the CST Studio Suite technological solution, starting from the classical RCS analysis through material design and handling, advanced analysis and diagnostics. And we'll discuss also about the benefit of having a real transient analysis. When it comes to radar cross-section, please allow me just to introduce the very well-known radar equation, right? In the monostatic configuration when transmitter and receiver are in the same location. Okay, in this little, very simple equation, you see a little letter, sigma, which is going to be the focus of this presentation and can be the focus of an entire career of an engineer. Okay, and we just mentioned the definition of monostatic RCS, but we can also have bistatic RCS or multistatic RCS, depending on how many transmitters and receivers you have and depending on where they are located. And as I said, even if RCS, it appears in the radar equation like a little letter sigma, it depends on several things, on several aspects, like target size and shape, material, frequency of your radio frequency sensor, transmitting and receiving angle, the polarization of your device, and also the load conditions for antennas. And with this plot, I just want to show you different values. I want to give you a feeling of different values, RCS values for different category of targets. Okay, and here you can see values in dB square meter or millimeter square. So target material, we said very important, was the second item in the list. And one typical solution for controlling the radar signature is indeed using materials appropriately designed to be transparent or reflective based on the frequencies, okay? And that's the typical case of a frequency selective surface or a radar absorbing material, which is normally designed to absorb your signal and reduce the scattering level, so the RCS. Frequency and aspect angles are also very important. For example, here for a PC flat body, you can see that the higher the frequency, the higher the monostatic RCS when we have a plane wave impinging normally on the plate. Field polarization was the other important item. You can see here just the difference between horizontal and vertical polarization for this target. So this can be also an important point. A very special behavior can be observed when we study the RCS antenna. In fact, an antenna is a device which is designed to radiate the electromagnetic field in a certain frequency band. And in order to do that, normally it is connected to a feeding network. And there is, with all the impedance, the relevant circuit, etc., etc. And this leads to the so-called antenna mode and structural mode. The structural mode is related to the antenna as an object, independently of its radiation properties, while the antenna mode is related to the energy that is captured by the antenna at its port and is reflected back depending on the load or matching conditions. Okay, and in this polar plot, we can see the effect on the RCS when we have two different load conditions for this array of Vivaldi antennas. Now that we've seen a little bit of challenges in the RCS prediction, let's have a look at the technological solution offered by SIMULIA Studio Suite. And in general, let's have a look at the benefit of using simulation in conjunction and synergy with physical testing. All the different factors which affect the RCS of a target lead to different challenges, as we said, that we as engineers, as scientists, we have to address. And this includes the ability to handle, for example, multi-scale structures. So complex structure with certain kind of materials with different geometrical features here and there. And in that regard, having a complete portfolio of numerical methods, which in the end is going to be your proper engine to resolve the Maxwell equation, is very, very important. And I can, say that our complete technology is really the key solution for this kind of challenges, for this kind of problem. As you can see, and as you have seen even today several times, we have different solvers, what we call the F solver, which is a finite element method-based solver in frequency domain. We have the time domain solver, which is actually not a single solver, but is a family of two different methods, FIT and TLM. Then we have the integral solver, which is a BEM method, and then we have the asymptotic solver when the model becomes really, really big compared with lambda, or when the frequency becomes actually very, very big, if you like. And this is the very classical plot, which shows us the different scattering regimes, the Rayleigh region, resonant region, optical region, okay? And here we are just looking at the scattering behavior of a sphere, and you can clearly see this sort of convergence when the frequency becomes very, very high and the model becomes big with respect to lambda. And let's take a real case just to have, to have a look at some nice animation and the very physical videos here, where we have this helicopter, which is 12 meters long. And we can see here how the behavior is changing based on the frequency. Okay, we have one case where the size of the model is pretty much 1 lambda, and then when it's bigger, and then bigger and bigger and bigger, where in the end we can distinguish several scattering centers on our model that will contribute pretty much independently each other, while the completely opposite case, where we have a very small object where everything is combined together, and when we also have some resonant behavior. Now that we have a clear picture of the several numerical methods available in CST Studio Suite, I'd like to illustrate how we can also make synergy among them, and in order to simulate models that cannot be tackled using one single method, or in any case, when using just a single method, is not, let's say, the most efficient thing to do. Okay, and in this regard, we will consider this mock-up model, which is a platform that includes a cavity on top. And as I said, using the hybrid task, here we can define two different subdomains, and we can apply the right method to the different parts. Okay, in this particular model, we are using the integral solver to get the scattering from the cavity, while for the platform itself, which sounds like the nose of an aircraft, we are using the asymptotic solver. And in this polar plot, you can immediately see the importance of actually using the hybrid approach, because clearly in the red curve, the asymptotic solver alone is not able to capture with a good accuracy the scattering from the cavity, which is something that we can do with the integral solver, and we kind of compensate the contribution of the cavity using the hybrid approach. And talking about big models and complex platforms, I would like to mention about the new features that we developed in the 2024 version. So it's already available for you, which is the uniform theory of diffraction, so UTD. The UTD is an extension of the Keller's geometrical theory of diffraction to get more accuracy in the modeling of scattering from edges and wedging, so the diffraction contribution. And in this picture, you can see how we can nicely illuminate the shadow region, and we can capture the scattering from this horizontal wedge using the UTD. In the asymptotic solver, the first order diffraction contribution has been always there, okay, available using SBR and PTD, the physical theory of diffraction. However, the further propagation of diffracted rays can be considered only using the uniform theory of diffraction. That's why we introduced UTD in this latest version, because in this way we can include additional higher order phenomena like diffraction plus reflection, or diffraction plus diffraction, and so far so on. Let's have a look at a realistic model here, which simulates basically an aircraft tail. Okay, and in here, basically, I started including the diffraction contribution with the PTD, and I'm comparing this contribution with a pure SBR approach. Then you can see that at the end, I'm also including the uniform theory of diffraction. And if I now get rid of all the rest and I only leave these two curves, you can clearly see the benefit of using the UTD in terms of accuracy here, okay? As a reference, I'm using the result that I have computed using the integral solver, so with a full wave method without any assumption, without any approximation. And let's say for sake of completeness, I have to say that still in 2024, we also introduced the possibility to calculate the higher order PTD contribution. So UTD, it's a new feature we introduced. PTD has been always there, but now what I'm talking about is also an improvement on the PTD, which is the higher order PTD, which means that besides the contribution from edge and wedge that are directly illuminated by a plane wave or by our electromagnetic source, we can also include the diffraction generated by rays reflected by the patches, for example, or diffracted by UTD rays. Okay, that's also a very nice improvement in terms of accuracy and capability to catch the right behavior. And still talking about new features in the RCS world that we introduced in 2024, let's have a look at another important thing, which is the geometrical symmetry. The geometrical symmetry, it's very, very important when we are dealing with models that are geometrically speaking symmetric, but they are not from the point of view of the source. So for example, let's suppose we are impinging here with a plane wave, which doesn't have, for example, a particular geometrical configuration with respect to the main planes. Using the geometrical symmetry, we can now do it. And if we consider the example of this aircraft, which is 13 meters of wingspan and 4.7 meters in length, we can see that we can calculate the RCS. Here I've chosen 1 gigahertz, and I'm spanning from 0 to 180 with a step of 0.1. And you can see here the comparison between the full 3D model and the application of geometrical symmetry for HH polarization and VV. So basically, we are not losing anything in terms of accuracy. And the great news is the big advantage, really, really big in terms of memory, especially, and also in terms of time. So we can get the same results much faster and with much less memory. So that's a very, very nice improvement that we did in the latest version. And after this, let me say, brief description of the CST Studio Suite technical offers, let's now deep dive a little bit more on the radar signature prediction and all the typical problems scattering, say, engineer, scattering expert has to deal with. And so here I just want to give you an overview of different analyses that you can run with CST, how you can do it. Like here, you can see the monostatic RCS of a helicopter, 12-meter length, which is something like 40 lambda at 1 gigahertz. And for this simulation, I use the integral solver, calculating 721 different monostatic values for horizontal and vertical polarization. So it's a massive amount of data to be computed. And also for the automotive market, you see there is a big improvement. There is a lot of interest in the ADAS world. So 77 gigahertz. So easy task for CST. Use the asymptotic solver. We can easily calculate all the monostatic points here at 77 gigahertz for car. And even bigger, here we're talking about a platform of 1,600 lambda, where we have calculated, again, 721 different monostatic points at 12 gigahertz. And for people that maybe are wondering, are these results accurate, especially when we use the asymptotic solver with this, the typical assumption of the asymptotic approach, so large compared with lambda. So answering that question here, you can see the difference between a proper full wave method, which is the integral solver, and the asymptotic method, which is very, very accurate, fast, and efficient, of course, when the size of the model are big compared with lambda. And I already briefly mentioned about the effect and the importance of having different materials in the application of the materials. So let's have maybe a closer look. CST Studio Suite offers dedicated tools for the analysis, design, and optimization of different kinds of materials. And whether we are talking about metamaterials, radar absorbing materials, frequency selective surfaces, we always have an answer for that, and we have the right tool for simulating this kind of materials. And in particular, I want to show you here the workflow on this frequency selective surface, which has been optimized at 10 gigahertz using a genetic algorithm. As any optimization algorithm, it's an iterative process. And after a few iterations here, I got the convergence and I optimized this material to be pretty transparent at 10 gigahertz and to be, say, pretty reflective out of band. You can see that from the 1D curves on the top and the 2D plot on the bottom. And similarly to the case of the FSS, I've also designed a radar absorbing material here at 10 gigahertz using the same approach. So again, I started from this layered structure, as you can see here, and I optimized the structure to absorb at least 10 dB at 10 gigahertz. Let's see how you use that in practice. So first stage, optimize the material itself, and then the installation on the platform. As you can see here, there is a comparison between let's say, a full metallic model versus the model where I applied this radar absorbing material. Okay, and you can see immediately the reduction of RCS, especially where the leading edge was important. You can see the application on the leading edge because of this light over here. Okay, and the same consideration we made analyzing this last RCS plot helped me to introduce the next topic, which is in general, after the calculation of the RCS itself, how can I understand a little bit more about what's going on my model? I need some advanced tool and I need some diagnostic analysis to really understand. And the first diagnostic tool here that I want to present is the range profile. The range profile is a particular kind of analysis that allows us to identify different scattering centers and place them on the target's body. Let's suppose we have calculated the monostatic RCS pattern and we see some peak, strange peak, or anyway, a peak we really want to verify the where is this coming from, okay? First thing we can do, we can run a range profile simulation and we can locate all the different peaks, as you can see in this plot here. Now it's a little more evident to identify and distinguish the different scattering centers. Here you can clearly see, for example, that the main contributors are the nose of the aircraft, and then we have the wings, and then there are the rotor blades and the tail of the aircraft, etc., etc. So, of course, it depends on the point of view. If your point of view is reducing the scattering, reducing the RCS, of course, you want to go there and see how you can reduce the contribution from these particular main scatterers that this range profile analysis has highlighted for us. Okay. And when we collect several range profile, then we talk about sinogram. As you can see here, the sinogram, it's simply the collection of several range profile, which gives us this very typical hourglass shape that you can see in here. Okay. In conjunction with the range profile and sinogram, we can also use the hotspot analysis. Same concept, similar consideration, but different outputs and different kind of analysis. In particular, with the hotspot analysis, we can really place on the 3D model, we can identify where are the main scatterers. And again, let's consider this polar plot here, monostatic RCS for this aircraft. There was a strange peak here in this plot, and I said, all right, so let me deep dive a little bit. Let me understand why do we have this peak here, because it was not that clear at first sight. So that's around 118 degrees in the horizontal plane. Okay, so I said, let me run a hotspot analysis. And the result of the hotspot analysis, as you can see, is this qualitative plot where we can see what are really the hotspots, so the main contributors for the RCS. And this can be done for one single aspect angle or can be done for different aspect angles. So to have a full picture and a clear understanding of what's going on. Let me show you another important diagnostic analysis, which is available for the asymptotic solver. As you know, the asymptotic solver is an SBR method, shooting and bouncing rays. So if I calculate the rays and I have the possibility to visualize them, that's certainly a very good plus. Why is that? Because I can easily understand where this contribution is coming from. Is it just a first order reflection? Does it come from multiple bounces? Then can I optimize something in my shape to perhaps reduce multiple bounces, reduce corner effects, which normally gives us very high RCS, pretty wide beam. So all these kind of considerations can be done. And another diagnostic tool on top is the inverse synthetic aperture radar analysis, which is again a sort of 2D extension of the range profile we have seen already. And again, it works exactly in the same way. I have my model, I calculate the RCS, I see something strange. So I start learning about what's going on my target, and I run my range profile, I run my hotspot, I can check rays, I can run the inverse synthetic aperture analysis here. And the result, as the name of the analysis already says, it's an image. Okay, and it's really a picture of my model. But in this case, the sensor is not actually an optical camera as we normally use, but it's a radio frequency sensor. As you can see, I have calculated this ISAR image at 5 gigahertz for VV polarization. And now I can clearly see who is the responsible of that peak in the RCS. So where this peak is coming from for different aspect angles, 67 degrees, 158 degrees. And I can immediately identify, for example, the nose and the blades of the aircraft as main contributors, okay? And here I'm just showing different ISAR image for this helicopter. And it's also, I say, pretty interesting to see that we can calculate this range, cross-range azimuth on the left-hand side. When I say cross-range, I can distinguish between cross-range azimuth and cross-range elevation, okay, that we see on the right-hand side. And here there are also other radar image for this helicopter for different aspect angles, phi azimuth 90 or 165. Okay, so all these additional diagnostic tools to really understand. And that's not all. Let me show you something else, induced currents. As you perfectly know, the RCS, it's an integral. So it's a global information that we get. But let's go now local. And we have been already pretty meticulous on studying locally our targets, hotspot, ISAR, range profile, rays, etc., etc. Induced currents. That's particularly suitable when we use the integral solver. Why? Because it natively calculates current. So the currents are the basis, let me say, for us to calculate then the scattered field. So let's study the currents and let's see immediately, let's have a look at them and let's see if we see something strange, if we can understand something. But as I said, sometimes it's not very clear to immediately have a look at the induced currents and being able to say something about the scattering. And for that reason, we developed a new feature recently, which is scattering by subgroups, where we can basically separate different contribution coming from different parts of our platform. And we can say, all right, that RCS value, it's coming mainly for this part. And normally the problem of that is that the integral solver is anyway a full wave simulation. So it takes some computational effort. And we would like to do that in post-processing. And that's what we can exactly do now with the new version. So we can wisely split the model before running the simulation so that after running the integral solver simulation, we have different currents for different parts of our model. And then in post-processing, so without running the simulation again, and that's the beauty and the power, we can say, okay, so if I let these currents now radiate, this is the RCS value that I get, et cetera, et cetera. In this particular case, it was very, clear to see that the responsible for that peak in the RCS plot, it's actually the leading edge of the aircraft, okay? Now, of course, the expert engineer can already have a feeling, but this is a very rigorous way to do it, okay? So you take your currents and you can run the scattered field in post-processing. And as I said, you don't need to rerun the simulation from the beginning. You just need to define a template-based post-processing. And this takes me to the last topic today, which is running a real transient analysis. You know that CST Studio Suite, it's the software package that provides the best time domain solution. And for that reason, I cannot avoid to mention that. And with our robust PBA meshing algorithm, which you have already seen today, I'm not going to spend too much time on that. But what I want to mention is that with a real transient analysis, you can do a lot of things. It's certainly a big plus on that, because you can really see what's going on from a very physical point of view on your model. But very nicely, you can do what we call time gating. So you can really observe the time domain signal, which is, time and space in RCS, they're basically the same thing, just because, delay means space, means range, means possibility to highlight the main scatterers on the target. And that's exactly what we're doing here with the NASA Olmot. I have time gated the signal, which is coming from actually the creeping wave here from the back of the NASA Olmot. And I'm comparing here the RCS coming from the creeping wave with the analytical formula here of the tip. So I'm excluding actually the creeping from the back. I'm taking the contribution from the tip, and that's what I'm comparing here against the analytical formula of an ideal cone, okay? And that's really the conclusion of my presentation. So we have seen several things today, right, about RCS simulation. Let me summarize them a little bit. One of the main challenge here we have highlighted is the need of having different numerical methods that can interact each other, and potentially even with a hybrid approach. We have seen how we can calculate RCS, we can design material, we can verify installation performance. We paid particular attention on how we can use advanced diagnostic tools for a deep and complete understanding of our targets. And if we all agree that all those points are important, certainly CST Studio Suite represents the right tool for engineers that have to deal with these kind of problems. And that's all from my side. Thank you.